Good morning to everyone. So when we were in college or university or school times, generally what happened is that, or till now it is happening, is that in the morning times there are some theoretical classes, and in the afternoon times it will be some experimental handwork. So in this session, Professor Banerjee has given a good theoretical understanding of how the narrowband chaos occurs in mechanical impacting systems, what's the reason behind it, and all. So now it's time for a little bit of experimental observation. I am Dr. Somojit Seth. I am now currently working at UCD as a postdoctoral researcher under Dr. Vikram Pakrasi. I am a nonlinear dynamics, but from experimental point of view. I do work on electronic circuits and systems. The beauty of electronic circuits are that it is very inexpensive and easy to implement. So if you need some tune the parameter or vary the parameter, you can easily be done using the experimental circuits. So today I will talk about all those experimental observations that we can anticipate or we have got already. Because Professor Marian yesterday showed his experimental strand where he got some bifurcation behavior like narrowband chaos and all. So I will try to show all those things, but from experimental point of view. So my outline of the talk is will be like introduction, like basic things of impacting mechanical systems, but Professor Banerjee has already told many things. Then what is already known in those areas, literature reviews, then equivalent electronic circuit of mechanical impacting system. First, I will tell 1 degree of freedom systems, then I will go forward for 2 degrees of freedom systems, because 2 degrees of freedom systems, the system that I worked that has not yet been matured. So then numerical results, experimental validations, and future directions. So this is a schematic representation of forced damped oscillator with a massless impacting wall. And this mass is attached with this hard surface with a damper of damping coefficient R1 and a spring with spring constant K1. Here we are applying an external periodic force, which is a sinusoidal force having an amplitude A, and the angular frequency is omega. U is the displacement. So if we apply a force here, what will happen? Two things will occur. First, it will oscillate, but it will not hit the impacting wall. And second condition will be it will hit the impacting wall, and accordingly, depending upon the stiffness or depending upon the spring constant value, it will move back and forth. So when it does not hit the impacting wall, mass does not hit the impacting wall, then the equation will be like this: a simple mass spring damper equation with a sinusoidal external periodic function. And when it will hit the impacting wall, the equation will be like that. Please note that the stiffness ratio, which is a non-dimensional part, which is the ratio between K2 and K1. Depending on the value of K2, the stiffness ratio will vary. When K2 will be large, beta will be high. Otherwise, when K2 will be low, beta will be less. And the M, which is kind of a relation with non-dimensional frequency, which is twice of natural frequency divided by systems or applied frequency. So in literature review, Nordmark showed that here one of the element in the Jacobian matrix goes or diverges, and that's why there is a local stretching in the phase space, and this is called the singularity. Also, it has been shown that the attractor or narrowband chaos, which will occur here, its Poincare structure will be like a finger structure, and when the M value will be non-integer, there will be a narrowband chaos at bifurcation point or impacting condition, and when M will be integer or close to integer value, there will not be any chaos. And Professor Marian, they have done an extensive work on mechanical impacting oscillators, and they have verified all those phenomena. But for electronics, what will happen is that you have a little, you will have a room, a simple breadboard, you have some ICs, and you can do many works by varying all those parameters and values. And not only that, you can vary the parameter values very easily. So, my question is, can an electronic circuit act as an analog of an impacting system? This question I am going to ask. So the equation that is governed by this schematic representation of 1 degree of freedom mechanical impacting system, that is this. So the force voltage concept that is used in mechatronic engineering is that the mass will be replaced by an inductor in electronics or electrical circuit. The displacement U will be replaced by the charge stored in the capacitor. The damping coefficient will be replaced by the resistances, and the spring constant will be replaced by the reverse of the capacitor value. So we have done this 1-to-1 correspondence and have got this equation. And the distance between the equilibrium position of mass and the impacting wall is we will define as a reference voltage, which is kind of DC voltage. So this is the equation. Now we want to make this equation in a circuit form. So this is a simple RLC circuit. This switch defines whether there will be impact or not. This and the switch means there is an input, there will be output, and the switch will be controlled. So this control will depend on the comparator output. When the comparator output will be high, switch will be on. When the comparator output will be low, the switch will be off. And the comparator output, which will depend on the differences between the plus, which means non-inverting input, and minus means inverting. And the inverting input is directly connected to the capacitor C1, and the non-inverting input is connected to the reference voltage. So when the VC1, which means the voltage across the capacitor is less than the Vref, this will be 0. No, this will be 1, and the switch will be on. And when the VC1 is greater than the Vref, the output will be comparator output will be 0, and the switch will be off. So when the switch is on, the system will be like simple RLC circuit with an input which is kind of a function generator. In electronics lab, you will get this function generator easily, and this will be a sinusoidal voltage. And when the voltage across the capacitor will be high of Vref, then the switch will be off, and the parallel capacitive branch will come to an exist. And this system will exactly mimic this equation. And here the stiffness ratio is nothing but the ratio between these capacitor voltages. When C2 is less, beta will be high. When C2 is high, beta will be low. We made this circuit in a real breadboard. But yeah, before that, I want to tell the numerical part. So we have done the MATLAB simulation from the differential equation of this thing, this equation, and we have got that we have anticipated that it has been anticipated that there will be narrowband chaos here and the finger structure here. But all these are from numerics. Now we have done the real experiment in an electronics lab, like breadboard, CRO, power supply, function generator, all we have, and we have captured here the trace of the capacitor voltage, in amplitude of the input voltage, reference voltage, and the comparator output voltage. Green one is the V reference voltage, which is a DC voltage. The sine wave is the voltage across the capacitor, and the purple one is the comparator. So when the voltage across the capacitor is less than the reference voltage, which is kind of before impact or there is no impact, so the comparator output is on and the system will behave as a simple RLC circuit. But when the voltage across the capacitor just touch the reference level, so you will find that the comparator output changes erratically. there is no pattern. And this is the chaotic waveform that we anticipate during the blazing condition or impacting condition. And after that, you will find that that is a period 2 orbit that we anticipated in numerics as well. So comparator output changes its states after 2 loops. Like this loop does not hit the reference voltage, and this loop had touch the reference voltage. Now we have obtained the bifurcation diagram directly from CRO screen, and we have found that so there is a large amplitude chaos, and it has been obtained in a very good manner, very good way. We made the circuit, and we are tuning one parameter like input amplitude voltage, and we are getting this narrowband chaos here. And the point intersection of narrowband chaos experimentally we obtained is this kind of infrastructure. So I can show you the video how the point intersection will look like. So you will find that the narrowband chaos will occur in that way, that Professor Banerjee was telling that the stable fixed point, although it remains stable, but due to its basin of attraction becomes 0, the orbit will means there will be jump in the state space. So that's why you are getting this kind of finger structure. So we have obtained this phenomena in experimental electronic circuit. And also we have verified this condition that there will be no narrowband chaos. Yeah, it's fine. Then we have done another type of work. We are now varying the capacitor voltage, which is added in as a parallel capacitive branch, which is nothing but equal to which is nothing but similar to changing the stiffness value from low to high in order to make the stiffness ratio from low to high value, which means from very soft impact to the hard impact. So when the stiffness ratio is very small, you will find there is a period 3 orbit, which will come to an exist. This is the Poincare representation, and the x-axis is the voltage across is the current, and the y-axis is the voltage across the capacitor. And as you change the parameter, you will find that the narrowband chaos will occur prominently, and its shape and the size will increase, and it will remain very small region. That also has been anticipated in theory as well. So these beta values we have varied, and m value is as a non-integer value. So we obtain this as in experiment as well. So from 1 degree of freedom system, it has been already theoretically, numerically, experimentally verified that there will be large amplitude chaos oscillations will occur. So now the question will come that what will happen if we increase this as a 2 degrees of freedom system, impacting mechanical system? Will there be any narrowband chaos, finger shape attractor? All those things will occur. That's the question we are going to ask. For that, we have considered this schematic representation of a 2 degree of freedom mechanical impacting system. We have designed the system not in experiment, but in numerically in order to make our electronic circuit experiment easier. Means we can make a real mechanical system and can do the experiment as well. But the problem will be that we need to have introduced many ICs and all. So when we will implement this in a real mechanical experiment, maybe we will not consider this exact system, but we can change a bit. So here we have used two masses, and their displacement is x1 and x2 respectively, and that's why it's a 2 degrees of freedom system. And this mass M1, which is attached with this hard surface by K1 spring constant value, and C1 is the damping coefficient value, and those two masses M1 and M2 are attached by a spring constant, and this mass M2 is attached with the hard surface by a damping coefficient damper having the damping coefficient C2, and there is an impacting wall which is added with the mass M2 with K2 and with spring constant K0 and the damping coefficient C0, and the delta is the initial separation between them when there is no force applied. So now we are applying a sinusoidal force here in the mass M2, And these are the governing equation when there is no impact, like they are not hitting to each other. So the equation will be simple, like this equation. When there will be an impact, so this will be this kind of equation. So we have done the non-dimensional form of this equation, and we have got two natural frequencies value back, as these are the 2 degrees of freedom system. These are xi1 and xi2 are the non-dimensional damping coefficient. Xi0 is a damping coefficient which is attached to the impacting wall, and there are some values, and the main value will be non-dimensional frequency. So we are taking here as omega, which is the applied frequency, and divided by the addition of the two natural frequencies, which is 1 by m. So m is related to the non-dimensional natural frequency, non-dimensional frequency. Now we have shown that when m is m is non-integer, here also we are getting chaos close to the bifurcation value. I have not shown here explicitly all those phase portrait, but here this region is close to impacting condition. But as the beta value is low, so it is a wide range of values. So we are now, as this is a very preliminary start work, so we will investigate more this thing. And not only that, this chaotic region value, like if 1 degree of freedom system as well, it has a finger structure, but it is a kind of fuzzy behavior because the impacting wall, which is added to the mass, that is also moving. So both are moving, and that's why this fuzzy behavior is coming. If we stop one mass, this will be prominent finger structure. And when the mass m value is close to close to integer value, we are getting this kind of behavior. There will be no narrowband chaos, but there is a hysteresis loop. We don't know what is happening there, but we will investigate this in future. These are the other parameter values. So apparently, when m is non-integer, there is large amplitude chaos, and when it is close to integer value, there will be no chaos. So this thing as well, we have made the electronic circuit of it. This portion is the mass, denoted mass m2. This portion is mass denoted by the mass m1. And like before, these are the condition when there will be an impact or not, equivalent to the mechanical system. These are the equations. And we have shown that here also, when there is no impact, so this is completely period 1 orbit. After impact as well, the orbit is period 1, like in this region. But during the impact value, we are getting the chaos. This kind of lines are coming because the inductor current is changing, and that's why the surge is coming here. And also when m value is integer or close to integer value, like 2.1, we have made the equivalent frequency form, and we have shown that when there is no impact, the orbit is period 1, and when there will be impact, the orbit is still period 1. So we have not plotted here the Poincare section because there are some constant on the CRO, because the CRO should have some Z modulation as well. So we could not get it, but we checked for every values of amplitude voltage, and we confirmed that this is happening as another. So recently we published this work as well in nonlinear dynamics. So the conclusion is that due to the ease of experiment in electronic circuit, so we can make the mechanical impacting system in a very simple and convenient way, where we can obtain those impacting systems result. And also it has been shown that if we vary, or if we change the parameter from, or if we change the capacitor value, which means the stiffness coefficient, that as well, the shape and the size of the Poincare section of that chaotic attractor, which will increase while the beta will be from low to high. In future work, we are planning for analytically or numerically why this narrowband chaos happening for 2 degrees of freedom system as well, by obtaining the path following bifurcation diagram and those things. So the take-home message is that whatever we have impacting system, we can approximate all those mechanical impacting system in electronic circuit. And we can easily obtain all those bifurcation behavior or some dynamical behavior in electronics system as well. So thank you for your attention.